This is EE698I, Mixed Signal IC Design, and this is lecture number 20. In the last couple of classes, we have been looking at the flash ADC. And in the last class, we saw how to tackle the effect of offset in latches. And we saw that if this is a latch, and if it has an offset due to any kind of mismatch, this can be suppressed by having a preamplifier before, right? And the preamplifier itself will have its own offset, and this can be auto zero. And we also saw that an alternative way to correct for this offset is to do some kind of calibration, right? That will counter the mismatch that is existing in the latch. Okay. And of course, you can do a combination of the two, wherein you can also have a calibration for the latch and then also have this preamp. Okay. And please note that this preamp not only helps us in reducing the effect of the offset in the latch, but it also increases the overall regenerative gain of the entire comparator. Okay. And for the latch, we saw one popular architecture is the strong arm latch. So where we essentially had a differential pair, and the current was then given to this back-to-back connected inverters, right? So we have two switches that reset the output and the intermediate nodes. Okay. And in practice, we have we implement all of these switches using PMOS switches, and all of them are clocked by the same clock 5 2. Okay, this is one advantage with the strong arm latch, that you just need one clock phase. And for the preamp here, we can have any number of variants, and usually we go for a simple single stage differential amplifier. So you could either have an NMOS differential pair like this, and at the drain you can have simple resistor, or you can also have a PMOS current source load, right? And of course, in this case, this gate voltage of this PMOS current source must be connected to some bias voltage, and this bias voltage will be set by a common mode feedback circuit, right? And this common mode feedback circuit will monitor the common mode of this output and tweak this bias voltage, right? This you might have studied in your analog VLSI course. Let me just write it clearly. Okay. Either of these two can be used for the preamplifier, but these kind of amplifiers have a small problem, which is the following. If you look at the latch here, when phi 2 is made 0 in the steady state, what will happen? This transistor is off, and all these nodes are pulled to VDD, right? So there is no current flowing from VDD to ground. So the latch does not consume any power. Similarly, when phi 2 is made high in the steady state, which means after a long time, what will happen? One of these outputs might be at VDD and other might be at 0. So let's say this is VO1 and VO2. So let's say VO1 goes to VDD and VO2 goes to 0, right? So again, because this is at VDD and this is 0, there is no path for the current to flow from VDD to ground, right? Because this is at VDD, so there cannot be any current flow. This is at ground, but remember this voltage is at VDD, so this PMOS is off, right? So there is no current flowing in the steady state when phi 2 is high. So when does this latch consume current? It consumes current only when the clock makes a transition, right? So when say phi 2 transitions from 1 to 0, what will happen? Well, at the end of the phase when phi 2 was high, say V1 is at VDD and VO2 is at 0. Now, when phi 2 is made low, these transistors, they will try to charge all of these 4 nodes to VDD, right? So V1 was already at VDD, so no problem, but VO2 and these 2 nodes would have been at ground. So which means these 2 switches will try to charge the parasitic capacitors at these nodes, right? From 0 to VDD. And only during this phase, current will be consumed, right? Similarly, when the clock makes a transition from 0 to 1, that is when the latch is made active, that is when this transistor will start to conduct and current will be drawn, right? But in the steady state, as we saw earlier, one of them will go to VDD, another will go to 0. Okay. So in short, this latch consumes only a dynamic power, right? And it has 0 static power. On the other hand, if you look at these preamps, they all consume a static power, right? Because we have this current sources at the bottom. So if you do not want the preamplifiers to consume static current, another variant where we again have the NMOS differential pair and another transistor at the tail. We again have the PMOS devices at the top. But instead of using them as current sources, we will use them as switches. Okay. So now here, when phi 2 is low, right? Let's say phi 2 is made from high to low. This it goes from 1 to 0. What will happen? Here we'll have capacitors, right? This could be some explicit capacitors that you add, or it could very well be the parasitic capacitors at this node, right? And when phi 2 is made 0 from high, what will happen? This transistor will turn off, right? And these 2 PMOS transistors will turn on, and they will reset or charge these 2 capacitors to VDD, right? So essentially, we'll have the current drawn from the supply to charge the capacitor, right? So only when we are making the transition from 1 to 0, we'll have the current consumption, right? And that is, this current is consumed only to charge these 2 capacitors, right? So finally, when phi 2 is at 0, if I call these 2 outputs as V1 and VO2, both V1 and VO2 will be reset to VDD, right? And this transistor is completely off, and this portion is completely inactive. Okay, so now let us say phi 2 is made high. What will happen? Now these 2 PMOS transistors will turn off, and this will turn on. So the equivalent circuit will look something like this. So this will be high, and at the top, the 2 PMOS transistors will be off. So we'll just have these 2 capacitors here, right? So let me just call them C0. And let's say the input is some VCM plus delta VI by 2. Here it is VCM minus delta VI by 2. So now what will happen? If let us say when this transistor is on, if the current it takes is some IB, what will be these 2 currents, I1 and I2? Well, I1 will be IB by 2 plus GM delta VI by 2, right? And similarly, I2 will be IB by 2 minus GM delta VI by 2, right? So how will the output voltages VO1 and VO2 look like? So let's say this is the time axis. And let's say at this point, we make phi 2 active, right? So when phi 2 is low, let me draw that here, phi 2 is low here, and phi 2 is high from here. When phi 2 was low, both VO1 and VO2 were reset to VDD. So the output will look like this till phi 2 is low. And once phi 2 is made high, we have these two currents I1 and I2 getting pulled out of these two capacitors, right? And as a result, these two voltages will start to fall down. And since I1 is greater than I2, VO1 will fall at a faster rate compared to VO2, right? So we'll have the scenario like this. So VO1 will fall faster compared to VO2. Okay, so this is VO1 and this is VO2, right? And you can clearly see that as time progresses, the difference in the output also starts to increase, and this way we get the amplification, right? And we see that if the input here is constant, we have the output dropping down linearly as a ramp, right? So which means this essentially acts like an open loop integrator, right? Because for a constant input, we are getting this kind of a ramp. Okay, and this kind of amplifier is also called dynamic amplifier. Again, because it consumes current only when the clock makes the transition, right? Either from 0 to 1 or from 1 to 0. Okay, and here you see that the differential output, how will they look like? So let me push this slightly to the side. So if I look at the output voltages, how will they look like? VO1, that will be, or if I just directly write the differential output, VO1 minus VO2, how will they look like? That it's going to be the differential current GM delta VI. And this GM delta VI is discharging this capacitors, right? So we'll have GM delta VI by C times T, assuming delta VI is constant, right? So you can see that the gain is GM by C times T, right? So this is no longer having a constant gain, it's some kind of a time varying gain. Okay. And in the last class, we also saw that when we have the flash ADC, the output of all the comparators, if you put them together, it will be a string of zeros followed by some string of ones. And this is essentially what we call as the thermometer code. And to convert it to a binary equivalent, we can simply add all these individual bits, right? That will give us the binary equivalent. Okay. And we also saw that in the flash ADC, since we have a large number of comparators, we'll have some comparators much farther compared to the others. So the clock will reach at different time instants for each of these comparators. So for the comparators located at the farthest end, the clock will arrive after some delay. And this clock skew will create some bubbles in this thermometer code. And one way to eliminate the issue of bubbles is to have a sample and hold upfront, right? And please remember that this sample and hold is in addition to the sampling operation we'll be doing in the preamplifier or in the latch, right? So we'll have the sample and hold here feeding the input to say the preamp and the latch, and you'll have multiple copies of this guy, right? Depending on the number of bits you want. Okay, and usually the sample and hold will also be preceded by an input buffer. Okay, and of course here also after the sample and hold you will have an output buffer, right? And since in flash ADC we want to have a fast analog to digital conversion, these buffers will be simple source followers, right? So for example, at the input side you might have an NMOS source follower like this. So this will be the input, the output you take here, right? And the sample and hold will be a simple switch and a capacitor. And again, we need to have another output buffer. This will simply be another source follower, right? Again, we have now two choices. You can either use an NMOS or a PMOS source follower. So what do you think is a good choice? Please pause the video and think about it. Well, if you use an NMOS source follower here, so what will happen? You'll have the circuit like this, right? So let us say I give some signal Vi. So this consists of the common mode and the differential signal and the small signal. Okay, so the output here will be Vi minus gate to source voltage of this NMOS, right? So which means the output here, that will be this signal minus one more gate to source voltage of this NMOS, right? So which means we'll be having two gate to source voltage drops. So we'll be essentially losing this common mode, right? But instead, if we use a PMOS, what will happen? The circuit will look like this. You'll ground the drain, and then you'll have the current source at the source. Okay. So now if you look at the output voltage here, that will be this gate voltage, which is Vi minus VGS of the NMOS, plus the source to gate voltage of the PMOS, right? So we'll have Vi minus VGS of the NMOS plus source to gate voltage of the PMOS, right? And this will help us to restore the common mode voltage. Okay, so this is what is usually done. So we'll use a PMOS at the output if we use an NMOS at the input. Okay, so this will then go to our preamp, and of course, before going to the preamp, we'll subtract the reference, so we can have a reference subtraction circuitry. That is essentially a capacitor that is charged to the required reference. So say on phase phi 1, we charge it to the required reference. And in phase phi 2, we subtract and give it. And we'll have the preamp here, right? And this could be our dynamic preamp or static preamp, whichever you want. So we'll have something here. And then this, the outputs of this preamp will go to the latch, right? And again, this could be any latch. And one popular architecture is to use the strong arm latch. I'll not draw the circuit. I'll just say it goes to say a strong arm latch, right? And the output of the strong arm latch, you can give it to a flip-flop to sample and store the comparator output, right? So let's say I'll do this, right? And of course, you'll have multiple copies of this, right? And the output of all the comparators that can be given to an adder. Okay. And the output of the adder will have the binary equivalent. And again, a common architecture that is chosen for the adder is the Wallace tree adder. Okay. So this is our sample and hold plus buffer. This is our preamp. This is the latch and the succeeding flip-flops to resample the output. And remember that again, to compensate for the offset, what we'll have to do, we can either do a calibration here, right? And of course, using the preamp will also help in reducing the effect of offset. And one last thing here, when you use a dynamic preamplifier like this, notice that the auto zeroing technique will not work, right? Because the gain here, it's a time varying gain, right? So when we had a static preamplifier which had a constant gain, we relied on the fact that, so this is the offset, right? We relied on the fact that when we had connected the output to the input and feedback, the output is constant and equal to VOS, right? But here, if we have a constant input, you see that the output is going to ramp, right? So auto zeroing is not trivial to apply here. So what can be done to compensate for the offset of this dynamic preamp? Well, we'll do digital calibration, right? So we can take the preamp again. So let me just quickly show it here. Oops. Now let me show it here. So we can take the dynamic preamp. Okay, so here we have the PMOS switches. I'll just show them as switches like this. Okay. So what we can do is we can have a bunch of transistors, right, connected in parallel, right? And again, we notice that when there is mismatch, current in one of the arms will be higher than the current in the other arm, even when the inputs are equal, right? So what we do, we in this box we'll have a bunch of transistors like this. So I'll just show 3 of them. Again, they'll be weighted in a binary weighted fashion. So if this is some W1, this will be 2 W1 and 4 W1, right? And the gate voltages will be either connected to VDD or ground. And if this transistor is on, it will carry some current, say I1. If this transistor is on, this will carry a current 2 times I1, and this will be 4 times I1, right? And by turning the optimal number of transistors in these 2 arms, in these 2 branches, we can make sure that the current imbalance is accounted for. So this way we can calibrate and reduce the offset in this dynamic preamp. Okay. Now, although in the flash, the design is relatively simple because you just need to design one section and you just copy paste of this, right? But of course, as we already saw, as the number of comparators increases, or sorry, the number of the resolution of the ADC increases, the number of such copies will also increase, right? So if you want to increase the resolution by 1 bit, we need to have twice as many components as this, right? So this kind of restricts the resolution of the flash in practice to 5 to 6 bits, right? And notice that on top of having each of these, we need to do calibration or offset correction for each individual comparators and preamp, right? So because of all of these, the practical resolution of a flash ADC is often limited to 5 to 6 bits. Okay. So there are a couple of techniques which can be used to slightly extend the resolution of flash, and these were indeed popular in the earlier times. So let's quickly discuss a couple of them. So let's say we have this combination of preamp and latch. This is the preamp, this is latch, right? So I'll just show a single-ended case where we compare the input with a reference voltage, say some VR1. Right, again, we'll have multiple copies. I'll just show one below. So this is again comparing with Vi. And let's say the reference voltage is some VR2. Okay. And you will have multiple such things on either sides, right? And you'll have a lot of reference voltages depending on the resolution of the ADC unit, right? So if you, let us say, want to increase the resolution by 1 bit, you need to have twice as many preamps and latches, right? So in this case, let us say each comparator is comparing the inputs with some reference voltages like this, okay? Or let me show it with this gap. So in this case, let us say each comparator is comparing the input with some reference voltages like this. If you want to double the resolution, we need to introduce an additional level between each of these 2 levels, right? And let's say if I call this level as VR1 and VR2, this will be VR1 plus VR2 by 2, right? So in principle, what you need between any 2 preamp and latch, we need to have one more preamp and latch. So this will again be Vi, and this reference will be VR1 plus VR, and this needs to be given to the latch, right? Similarly, we need to have one here also, and one above also. Okay. Now, if you look at this, we definitely need the latch, right? Because that's what makes the final comparison. And if you want to compare it with an additional reference level, we need to have this latch for sure. But let's see if we really need this preamp here also. For that, let's look at the outputs of this preamp. If let us say this has a gain of A, the output here will be A times Vi minus VR1, right? And here the output will be A times Vi minus VR2, correct? Again, I'm assuming this to be having a gain of A, right? And here in principle, what we need, the output we need is A times Vi minus VR1 plus VR2 by 2. Okay. Now please notice that this this value is simply the average of these two, right? So instead of having a separate preamp like this, we can generate this output by taking the average of these two, right? And how can we take average? Well, we'll simply connect two resistors here, which are of equal value. So the in-between point will be the average of these two voltages, right? So this will give us A times Vi minus VR1 plus VR2 by 2. Okay. So similarly, instead of having a preamp here, we'll take the output of the preamp that was above and connect two resistors like this, right? So obviously, this is going to reduce the number of preamps we need, right? But the number of comparators will still be the same, right? And reducing the number of preamps is advantageous because if you think about it, the input is going to all of these preamps, right? So the total capacitance seen by the previous states, right, that is actually providing the input, is going to be dependent on the number of preamps. Okay, so if you reduce the number of preamps that is needed, that is going to reduce the capacitive loading at this node, right? So this technique was popularly used some time back, and this is called interpolating, right? Because we are essentially interpolating this in-between value from the two other or two extreme values. Okay. And here we say that we have a 2x interpolation because we are having 2 times smaller number of preamps compared to the latches, right? So this interpolation factor is essentially the ratio of number of latches we have versus the number of preamps we have. Okay, and of course you can also extend it to a higher order interpolation. That is, instead of generating only one intermediate value, you can generate multiple intermediate values, right? So we can have, say, 4 resistors like this, right? And this will generate 3 additional levels, right? So in this case, we'll have a 4x interpolation. Okay. So what is the drawback or downside to this technique? Well, ideally, if the preamplifier has a gain A, and if it processes a single-ended input Vi and compares it with a reference VR1, the output here must be A times Vi minus VR1, right? And of course, all these intermediate points, they go to a separate latch. And here also we'll have a latch. And we'll have a similar arrangement in the bottom side also. Right? So here we'll have a preamp, a latch. And all these intermediate points will also go to a latch, right? So here, if the difference Vi minus VR1 is large, and if the preamplifier has a high enough gain, then this voltage can easily saturate to VDD. Okay, and the moment that happens, all these intermediate points will not be of the required or correct value, and this will completely corrupt the interpolation operation. Okay, please notice that here this voltage becoming VDD might not affect the latches on the downside, because if this voltage is saturated to VDD, all of these voltages will also be very high, and all these comparators may give an output of 1, right? And of course, this will also give an output of 1, right? But this is not a problem, because if the input is greater than this reference voltage VR1, it is definitely greater than all the lower reference voltages. Okay, so this is not a problem for the lower side, but on the higher side, this is a big problem, because we still do not know if the input is greater than the higher side references. Okay, so this will completely corrupt the decision of the comparators on the top side, right? So what we need to do is to have a reliable operation with this interpolation, the gain of the preamp has to be restricted. So this restricts the preamp gain so that the output doesn't saturate. That is, the output of the preamp doesn't saturate. Also, here to get the intermediate voltages, we relied on the fact that all the preamps had the same gain, right? So for the 2x interpolation, we had voltages like this, Vi minus VR1 and A times Vi minus VR2. And when we took the average, we got the intermediate voltage, Vi minus VR1 plus VR2 by 2. Okay. But if the preamps had different gains, we'll not get this voltage. Okay. So again, this will suffer from the mismatch between the gains of the preamp. So for all these reasons, this interpolation is not commonly used nowadays. Now there is one other technique which was used in the earlier times. So to understand this technique, let's look at an example quantizer characteristics. Let's say we consider an 8-level quantizer. So I'll show both the positive and the negative sides. Right. So essentially we have 4 codes in the positive, 4 codes in the negative side. Right. This is the input voltage and this is my output code. Right. And how are these output codes? If this will be 0, 0, 0, this will be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Right. So now let us say I have a 2-bit ADC that can realize this characteristic. Right. Only the positive side it can do the digitization. So I'll just show a differential input like this. Okay. So the idea is the following. If you already have a 2-bit ADC that can realize this characteristic, what we can do is we'll first find if the input is positive or negative. If the input is positive, we'll feed the input directly, right? So if we'll give the input and find the sign, and if the input is positive, which means the comparator output is 1, what we'll do, we'll give the inputs directly to the 2-bit ADC, right? And whatever 2-bit values it gives, we'll append this one, right? Because you see that the MSB here is 1 for the positive values of the input, right? So MSB essentially gives you the sign of the input. And if the comparator output is low, what we do, we'll flip the input, right? So instead of giving the negative input, we are going to give, instead of giving the input directly, we'll give minus VI, right? So since here VI will be negative, minus VI will be positive, and this can digitize and get the undigitize the input properly. Okay, so what we are doing essentially is the following. If the input is positive, the output is fed directly to the input. But if the input is negative, that is when the input lies in this range, we flip the input and give only the positive or the magnitude of the input, right? So if you want to implement it completely, it will look like this. The inputs are first given to a comparator that decides if the differential input is positive or negative. And if the differential input is positive, what we do, we feed the input directly to the 2-bit ADC, right? So we'll feed the input directly like this. But if the differential input is negative, we'll have to flip and feed the inputs, right? So we'll have, oops. So we'll have 2 switches like this, right? And this switch will be controlled by this bit. So let's say this is some D3. This will be D3, right? So if D3 is positive, D3 is high, the input is positive, it'll feed the input directly. If D3 is 0, the input is negative, so which means we need to flip it and feed. So this will be D3 bar. Okay, so in this case, when D3 is 0, these two switches will be off. So we'll have this crisscross, right? So which means we are feeding the negative version of the input and give it to the ADC. Right, so this is appended to the 2-bit output that the 2-bit ADC gives, and this way, and 3-bit ADC can be realized, right? So the advantage is that for realizing a normal 3-bit ADC, we need a total of 7 comparators, right? But now what we are doing, we are having only a 2-bit ADC, which requires only 3 comparators, plus we are using one additional comparator for detecting the sign of the input. So we have 3 plus 1, only a total of 4 comparators, right? That's around 2x reduction in the number of comparators you need. And this technique is called folding ADC or folding technique, because what essentially we are doing is the input, when it was doing like this, we are making sure when the input is negative, we are folding this portion and making sure that the overall characteristics looks like this. Okay, but of course in practice you will find that we cannot exactly get this characteristic, because this is essentially a piecewise linear characteristic, right? And this kind of sudden, exact sharp transitions cannot be obtained. So in practice, when you try to implement, you will find that the characteristics has a smooth transition like this. Okay, and this sort of limits the accuracy of this conversion. And of course, this technique need not be restricted to a single fold like this. We can have multiple folds, wherein let's say the input is doing like this, going from this value to this value. Ideally, you would have directly given the input to the ADC, right? So this would have been the nominal output. But now what you do is you find if the input is greater than, let's say, these 2 reference voltages, and if it's greater, you fold it. That is, this portion is flipped over. So you'll have the output like this. Similarly, once it exceeds VR2, you do something like this. Oops. Okay, and to do this, we need to compare the input with 2 reference voltages, right? Instead of simply comparing it with 0, wherein we just found the sign of the input, right? So instead of comparing the input with 0 to find the sign, here we need to compare it with these 2 references. And of course, you can have a combination of this folding technique as well as the interpolation also. And again, this was popularly done in the olden times. In the modern times, this has not gained a lot of traction because we have a pipeline ADC, which are much more efficient in improving the resolution without compromising the speed. Right? So we'll discuss about this, discuss about pipeline ADCs in the future classes.